For decades, physicists believed certain particle interactions simply evaluated to zero, not because nature demanded a void, but because the mathematics collapsed under its own weight. Now, AI assisted symbolic reasoning has uncovered new simplifications in gluon scattering, problems that have bruised the greatest human minds for years. We are not breaking the laws of physics, we are revealing the hidden structure that was already there. Today, we bridge the gap between the confusions of the particle zoo and the emerging precision of machine intelligence. To understand this breakthrough, we must first meet the fundamental cast of characters that build our reality. Everything you see, the stars, the earth beneath your feet, even your own body, is composed of particles called fermions. These are the building blocks of matter. Defined by a property called half-integer spin, fermions obey one of the most profound laws in quantum physics, the Pauli exclusion principle. It states that no two identical fermions can occupy the same quantum state at the same time. This quiet rule shaped the entire universe. It prevents matter from collapsing into a single point and allows atoms to form a stable structures. Fermions are divided into two families, quarks and leptons. Quarks are the social particles of the quantum world. They come in six flavors: up, down, charm change, top, and bottom. But quarks carry a peculiar property known as color charge. These are not literal colors, they are mathematical labels used to describe how quarks interact through the strong nuclear force. Using an analogy from additive color theory, red, green, and blue, quarks combine in similar ways that produce color neutrality, sometimes described as white. Because of a phenomenon called default color confinement, a quark can never exist alone. Instead, they form composite particles called hadrons. Pairs of quarks form mesons, while triplets form baryons, such as the protons and the neutrons at the center of every atom. A useful analogy is a magnet. You can cut a magnet into smaller and smaller pieces, but you will never isolate a single North Pole or South Pole. Quarks behave in a similar way. They are permanently bound by the strong force. If quarks are the socialites, leptons are the loners. Of leptons, the first generation contains the electrons and its elusive partner, the neutrino. Electrons are light and stable, responsible for electricity and chemistry. Neutrinos are nearly massless and electrically neutral, interacting so weakly that trillions pass through your body every second without notice. The second generation introduces the muon, about 200 times heavier than the electron existing with its neutrino. Then comes the tau, roughly 3,500 times heavier than an electron, yet so unstable that it disappears almost instantly after being created. But these are all matters and they alone does nothing. Particles must interact. These interactions are carried by particles known as bosons, the force carriers of nature. Photons carry electromagnetic force that governs light and electricity. The W and Z bosons mediate the weak nuclear force responsible for radioactive decay and nuclear reactions inside stars. And then there are gluons, massless messengers of the strong nuclear force. They are the invisible glue binding quarks inside protons and neutrons. And it is here that our story takes its turn, because the mathematics governing gluons was long considered one of the most difficult problems in theoretical physics. At the fundamental level, protons and neutrons are bound together by gluons. These interactions are described by the theory known as quantum chromodynamics or QCD. But the equations governing gluons are notoriously complex. When physicists attempt to calculate how multiple gluons scatter, the number of mathematical terms grows explosively. For just 6 interacting gluons, the Feynman diagram expansion can produce thousands of terms. For decades, this created a severe mathematical bottleneck. There were glimpses of elegance, and one famous breakthrough was the Parke-Taylor formula, which showed that certain maximally helicity-violating amplitudes could collapse into surprisingly simple expressions. But most configurations remained stubbornly complicated. Human researchers sometimes required months to reduce a single expression. This is where machine-assisted symbolic systems entered the story. Instead of brute force calculation, the AI was trained on algebraic identities, symmetry constraints, and known scattering data. Rather than expanding equations endlessly, it searched for compact functional patterns. In several gluon scattering configurations, the system rediscovered known simplifications and proposed new compact representations that satisfied every requirement of quantum field theory. Importantly, it did not break the standard model. It did not overturn the quantum chromodynamics. It simply revealed hidden mathematical structures inside expressions long considered intractable. Physicists then verified these results using established theoretical consistency checks. Why does this matter? Because when calculations simplify, everything improves, collider predictions become more precise, simulations run faster, and theoretical explorations expand. In high energy physics, simplicity is rarely accidental. It often signals a deeper symmetry of nature, and symmetry is one of the most powerful guides we have in search for fundamental truth. Physicists were never wrong, as some exaggerate AI over humans. It helped remove the fog hiding the old ones. The sewing missions were called threat until tailors started using it. The tailors who stitch this consciousness need speed to establish themselves in this world. Progress doesn't come from discovering new truths. Sometimes it comes from seeing the old truths more clearly. If we value clarity over exaggeration, follow our journey. We separate signals of scientific discovery from the noise of viral fiction. Nandri, Vanakkam.